Hi, everyone. Thanks for joining the C2 Smart webinar series. My name is John Patinos. I'm a project manager here at C2 Smart. This presentation will be recorded and posted to the C2 Smart YouTube channel. If you have any questions for our presenter, you can feel free to type them into the chat box below. And during the last 10 to 15 minutes, I'll be reading the questions of yours to the presenter. We're pleased today to be with Professor Anil Yazici of Stony Brook University. Today, he'll be presenting on Link Criticality Index for Analysis of Large Transportation Networks. Professor Yazici, you can go ahead and start.
Hi, everyone. Thanks for joining in for this presentation. In this presentation, I'll be talking about my work with my PhD student. All the things that I'm going to show you is based on his dissertation, and he did most of the work to give the credit. The problem is link criticality is an important aspect of designing and maintaining transportation, all networks, but also transportation networks. And there has been measures formulated in network science, not necessarily considering transportation networks in specific, but in general, it could be applicable in multiple domains like energy, water supply, telecommunication, social networks. Actually, there has been a lot of new measures after Facebook, social media is there and people trying to understand how these networks are connected. But one of the issues about this topological measures, this network science, graph theory based measures is when it's applied into transportation networks, they do not necessarily conform to traffic flow dynamics, like nonlinear, particularly nonlinear performance functions. Just to give an example, if, in a social network you connect someone through a friend, if this friend disappears, then you can connect the same person from another friend and you'll have the same two links to do it. But in transportation networks, when links performance functions are nonlinear, and this creates issues when you use topological measures. That's why transportation researchers incorporate traffic characteristics like travel time, flow into criticality metrics, and mainly through traffic assignment. And generally, how this is done is first, it's network performance measure is selected. It could be total system travel time, or it could be, for certain ODs, the travel time between the ODs. Total system travel time has been, used more frequently. And then in the network, each link is removed. Each, link in the transportation network is removed one by one. And after each removal, traffic assignment is rerun and the results are obtained. And whatever the performance measure, let's say total system travel time, it's calculated after each link removal. And eventually links criticality is identified based on the network performance measure, how it increased after the link removal. The higher the increase in, say, total system travel time, the higher the criticality of that particular link which was removed. Of course, this becomes computationally costly, especially when networks get larger, because you have to do this procedure, link removal and doing the traffic assignment again for each link. When you have more links, as the number of links increase, you do it linearly more times. And also when the network is larger, the traffic assignment also starts getting more and more costly to run and get the results. So, and another point is link removal eventually may lead to disconnectivity in the network. So if transportation networks are generally very highly connected, but if a link removal results in an OD to be disconnected, then you cannot run traffic assignment, and these metrics do not give you any result because you cannot run the assignment. Then, as we will see later, there are case-specific metrics are introduced just for cases where there's network disconnectivity. But what happens is then you have two kind of metrics that you cannot really compare. The ones that work when there is no disconnectivity, and there is one only for case of disconnectivity. Then how do you compare those scores? And in like a very summary of it, topological measures based on graph theory, network science, applicable in multiple domains, relatively easier to calculate and interpret, like, connectivity. It's easier to even explain. Computationally more efficient because there are very good algorithms that can, calculate those topological measures very efficiently. But they do not take the congestion into account. Or if they do, then they have to divert from their computationally efficient and easier interpretation characteristics. And traffic assignment measures incorporate traffic flow theory, capture the nature of traffic and flow and congestion, but then require multiple assignments, the way I explained, and link failures may cause disconnectivity in network, and then maybe case specific and not unified. So there is a need for a computationally efficient criticality metric that will, take into account both traffic flow characteristics and also network topology, like redundancy, connectivity, and so on. So in this talk, I'll be talking to you about link criticality index, which we suggest, and what we do, more innovative in the sense that we calculate link criticality within a single user equilibrium assignment, traffic assignment. Rather than running it for every link removal, we don't remove any links, but we run only one user equilibrium and we calculate the link criticality. Sounds too good to be true, but in the sense that we use, of course, we use intermediate steps of user equilibrium assignment. Basically, we use one assignment, but we take track of each iteration. I will talk about how the iteration works, and we look at each the changes after each iteration in the flow, and we figure out the rankings from criticality from those changes. And first, we implemented in Frank-Wolfe algorithm, which includes direction finding and move size determination. I'm not going to go into details of traffic assignment, but the underlying logic we use when we look at these iterations is critical links are on the shortest path more frequently under user equilibrium iterations. Basically, if you're asked, like, which is from your home to your work or wherever you're going more frequently, which is the most critical link, you would name the route that you'll be using more frequently, because probably you're using it more frequently because it's the shortest path. So basically, if links are on the shortest paths between OD, so basically everybody is using those links and to get to where they are going, and most of the time it's the best link, so it has higher likelihood to be a critical link. And if similarly, if a link is serving high number of ODs or ODs with higher demand, maybe it's serving very few ODs, but these ODs are constitute a chunk of the whole transportation network demand. So we try to incorporate whether a link serves a high demand or a low demand. And also, if, for instance, for my case, I live in Long Island, when I go to New York, I can think of Long Island Expressway. And even though it gets very congested, it's still the best route, fastest route, probably the most critical route to get to New York from Long Island. The reason is, although it is like although the flow all increases on the link, it's still critical because the alternatives are not that viable. So we also incorporate this if a link is assigned consistently higher flow within iterations, despite the increasing congestion, like it's already congested, but the flow is still assigned iteration to iteration to these links, then we assume that it's more likely to be a critical link. And for the mathematical, how do we put it into numbers? And to explain how to account for this consistent addition of flow to links, if a certain link is assigned additional flows in subsequent iterations, despite the increasing link saturation, the link is more critical. And to represent this, we use the marginal cost. Basically, marginal cost is the change in the link cost with the increase of unit flow. And we normalize these marginal costs for each link based on travel times, because sometimes networks don't have homogeneous links. Some are longer or have different network link characteristics, such as number of lanes. So their link cost functions are different. So we normalize it with the travel time for each link. And for links which do not experience within iteration to iteration, for those who knows more about traffic assignment, not all the time the flow increases on a link. Actually, it increases only when the link is on the shortest path. So if a link doesn't experience any flow increase, we assign the marginal cost as the score for that link at that iteration. But if there's an increased flow from iteration n to n+1, we look at the additional flow that is assigned on this link and multiply it with the marginal cost, which gives the increase in cost with unit cost. So we multiply with the amount of increase in the flows. And eventually this is how we calculate the score, but still not the LCI, because in this picture, this equation has no component that incorporates connectivity or redundancy or network topology. So for this, we introduced two weights. One weight is for the demand level served by the link, and the way we do it is we calculate for each link, we calculate how much of the total system network demand that this link serves. Basically, which OD pairs it connects so that it has potential to serve. So in this way, this coefficient actually can be at most 1 for a link. If a link serves all the ODs in the network, then it will have the total on the top, total demand, and total summation of all the demands, total demand in the bottom. And similarly for alternative routes, what we do is we look at, we come up with the weight that looks at individual path travel times between all ODs and assigns a weight based on the OD. Just a quick numerical example. If there are two routes between two ODs, if one is 1 hour, okay, 10 minutes, the other one is 11 minutes, they should be almost equally weighted, because 10 to 11, if anything that happened on the link, you may jump to the other link. But if it's one route is 10 minutes, the other one is 1 minute, then the likelihood that the alternative route will be utilized is a lot lower. So they are not, they shouldn't be treated the same way as two routes, 10 and 11 minutes. So you differentiate this with large difference between the travel times, we introduce this metric, and it assigns a weight based on the path travel time. So basically, if a route takes far too long than the other, then it's assigned a very low weight. And eventually we come up with our link criticality index, including marginal cost, the increases between iterations, and also link these two coefficients that incorporates the level of demand that is served by the link, and how many this links based on the path, which the link lies on a path, and if whether there are alternatives of this path, and how viable these alternatives, in the sense that they have very close travel times compared to the path that this link is on. And the way to implement this in Frank-Wolfe algorithm is we basically don't do anything, don't change anything, but we do a pre-assignment that we enumerate all the paths between each OD. So this, the way this LCI, the way I'm talking right now, it requires path enumeration so that we can figure out all the ODs and the paths, then we can compare and come up with those coefficients that I mentioned you previously. And then for each iteration, we calculate marginal cost and the flow increases, and we calculate those coefficients in between within the steps, and at the very end, we calculate the LCI. So basically, after one user equilibrium, we have the LCI score for that link. So we did some test runs on two networks, and we compared our rankings with some select criticality metrics. These are the ones that we found in the literature and used or referenced more frequently than the others. So what you can find all, we didn't provide the whole citations, but efficiency index basically uses network efficiency measure, but combines it with some kind of traffic flow component. So it uses traffic assignment. So it's somewhere in between topological and traffic assignment based models. Travel time weighted between centrality. It basically uses between centrality, which is a topographical measure, but weights it, as the name implies, with travel times. Importance score and network robustness index uses traffic assignment, and also follows this link removal strategy. Also same for the efficiency index. And for our toy network, we have 2 O's, 2 origins, and 2 destinations. And one thing, the way we designed this is we just created this network just to test it. One thing we wanted to show is link 7, failure of link 7 causes unsatisfied demand between demand pair 3 and OD pair 3 and 8. So basically, when you break 7, then all of a sudden there's a disconnectivity in the network. And our results, again, link 7 is kind of important here. Here's our link rankings. Basically, we calculated the criticality scores for each link using different measures, including our own measure of LCI. And as you see, 7 is always on the top, except efficiency index, which shows it a bit lower. I'm particularly talking about 7 because 7 is in between. It serves all the ODs. It's a disconnected network. So one would expect that 7 would be on the top in terms of criticality, because this is the only link in the network. When you remove it, it creates this disconnectivity. But in that sense, network robustness index and importance score also puts them to the high up, but actually we put them high up because for network robustness index, NRI, the score is infinity, because NRI doesn't calculate any score when there is a disconnectivity. So basically there is no score for 7 because the OD demands are not satisfied. The score is infinity by default. So basically it cannot be compared with the other links because it's not even calculated. For importance score, there is another metric specifically for disconnectivity links. So its score is, as you see, it's lower than the other scores, which are calculated by regular importance score. So one of the problems as I discussed is when there's disconnectivity, it becomes difficult to compare the scores. Even sometimes it's not calculated. Even if it's calculated with a different metric, then it's a different metric that you cannot homogeneously compare with other links. And on the other hand, travel time between the centrality, second measure on the left in the table, 7 is on the top because between the centrality score of 7 is very high. It serves all the ODs. It's in the shortest path of almost all the ODs. So eventually it's ranked higher. And for LCI, it's higher too, because 7 is a very high score of this. When we consider the redundancy, alternative routes, we put a high weight on 7. Like there's a high weight on 7, so it's on the one of the top ranked links. And if we continue with the others to see how they look, for instance, IS, NRI, and AI ranks 3, 9, 8, and 13 on the very top, right after 7. And these links are at the top, some of them are top flow of links. And as you see it here, it's on the very top. But then again, travel time weighted between the centrality ranks them at the very bottom. The reason is these links don't have really high between the centrality scores. So eventually they don't make it to the top of the list, even when they are weighted with travel time. And in terms of LCI, as you see, we have our results somehow put some of them on the top, some of the bottom. And I want to show you another example for link 5, which is an important link because it is one of the alternatives in case between ODs in case the other links fail, and it has a high between the centrality, so it's scored higher. But if you look at the other metrics, it's not necessarily ranked on the high on the top. So basically, here one of the problems is I'm going to discuss more is there is no ground truth. So we don't know like whether LCI is better or like one of the EI is better. But what we observe is there's a discrepancy based on which metric to use. You can dedicate one, identify one link as critical or not critical at all. So there's this discrepancy, and we really don't know who is right. So, in observations, discrepancy in the metrics, no ground truth or consensus for benchmarking. That's a problem similar to travel time reliability metrics that, I had some works on it too. There are literature on this aspect as well. The same kind of, data, same link, one measure says reliable, the other measure says not reliable, and because there's no, like a binary failure and failure mode that you can say it's failed or not. So there's no really data for benchmarking and telling for sure that this is the best method or metric. And there is a high correlation between rankings and equilibrium flows. So, what this tells is why are we bothering ourselves with, doing all this rigorous, calculations, link removals. Instead, we could just look at the link flows. We can even measure it, and we don't even have to run traffic assignment and sort them by link flow magnitude, and the top one is the most critical. Why are we? Is this such a? If there's such a correlation, then all this on link criticality may be just an academic exercise, but nothing in practical. So, and rankings do not necessarily reflect the role of alternative routes or network redundancies. As I showed in this toy network, like some links are very critical. That they are the only alternatives if some of the links are lost, but they don't necessarily rank at the very top. So at first glance, I want to emphasize this. At first glance, LCI provides a balanced ranking because you see the links on the top, links on the bottom in other metrics. LCI provides somewhere in between. This is actually what we were also shooting for when we were formulating LCI, to both incorporate the flow. So, okay, high flow links, one may expect the high flow links will have higher criticality, but also where they are in the network is also important. So we try to incorporate too. So it's with this toy network, which doesn't say anything concrete, we're getting somewhere, it looks like. And then we implemented LCI on CFO's network to see this, flow correlation business, like whether the higher flow links always, ranked higher with the methods. So what we did was because each link, each metric score ranges are different, we normalize them from 0 to 1. Basically, we take the minimum, the maximum, we normalize everything in between to make it from 0 to 1 so that we can compare side by side. And here, as you see, we have, efficiency index, importance score, network robustness index, and travel time weighted in centrality. And for each graphs, what they show is each dot represents a link, and on the the y-axis shows you its score with the criticality metric, and the x-axis shows the flow the flow on this link at the final equilibrium. So basically the user equilibrium flows on that link. So if you look at the correlation coefficient, it's pretty high, 0.89, high correlation with the flows, which tells that maybe we shouldn't be even using these methods, because just ranking it with based on the flow. But if you look at travel time weighted between centrality, the correlation is not that high. We don't know, maybe if travel time weighted between centrality is more closer to truth, then maybe the flows, we shouldn't be using it. But if the other methods are closer to truth, then maybe we just rank the flows, don't even bother. This finding is similar to the finding in toy network, and for LCI we do the same, and our correlation is lower. which doesn't tell it's better than the others or worse. Again, it doesn't tell anything about superiority, but it's just a fact that LCI does not necessarily provide rankings that are with high agreement with the flow rankings. So computational challenges, LCI and travel time between centrality requires path enumeration. LCI by design and also travel time weighted between the centrality, because for between the centrality, it relates to how many times a link appears in the shortest path between all ODs, so there is a path enumeration involved in it. And the other methods require n plus 1 traffic assignments. N is the number of links in the network, and plus 1 is you do it for the base network, then you remove each link, do n more traffic assignments, and compare with the base network results. So it was 77 for Sioux-Falls. The runtime results were for Sioux-Falls. LCI runtime was about the same as TTWBC, but about 35% of the other. So almost 1/3 less time for Sioux-Falls network. So some intermission, because now just wrapping it up, compared to several select measures, LCI provides a balanced criticality ranking with respect to both traffic characteristics and network topology, avoids multiple traffic assignments and provide computational savings, and some metric, some metrics can be approximated by simply sorting user equilibrium flows. So now I want to be the devil's advocate and kind of ask questions to myself, like this balance ranking, is it really, like, how do we measure balance? Okay, we solve in a one toy network that the links that appear on the top and the bottom of the other ones are more in the middle. How do we measure balance, or is this generalizable? Can we say this for all networks? This balance ranking, criticality ranking part for LCI. And yes, for Sioux-Falls network it took shorter amount of time, but for a method which requires path enumeration, that may be too bold. Actually, it is too bold, because okay, for when the network gets larger and the number of links increase, yes, each link means that there's another travel time assignment which increases the runtime. But also path enumeration is very unfriendly. It is, the computational complexity is worse when it gets worse and worse as the network link number increases. So maybe up to Sioux-Falls, yes. Maybe later for larger networks, LCI may lose its computational advantage. And LCI rankings, like we show that for Sioux-Falls network there is very little small correlation with the flows. But is it wrong? Like, what if really in the networks the criticality is highly correlated with the flows? And also, is it generalizable? So this is kind of a story of how we moved on with our criticality index research. And major issue that was next for us. Like, there's computational efficiency problem. We know that path enumeration is very ugly as the network gets larger and larger. So we come up with two potential solutions. One is using a select number of routes instead of all routes, basically avoid path enumeration, and let's reduce a set of routes that we're going to use to calculate those weights when we're calculating the LCI. And Frank Wolf is one of the early algorithms for traffic assignment. It's very good, works very nicely, but it's not necessarily the best method computationally. So what we did was we first get rid of path enumeration and we select a viable route. So, and viable routes, the idea behind it is not, when you have the enumerated paths between ODs, not all the paths are practically feasible or utilized. If there's a very long detour between an OD, it will appear in path enumeration, but practically it will not be used unless most of the links fail, and then maybe it's a path on the periphery will be utilized. So starting from this, how we decide that a path is viable so that we can look at only the links on those paths. we looked at user equilibrium iterations, and if a link doesn't appear in any of the shortest paths, so basically we tracked the shortest path during the user equilibrium iterations, because what happens in user equilibrium is it assigns to a certain path. After this path travel time increases, over an alternative path, then user equilibrium assignment starts assigning, demand to the alternative path. Then after these, both travel times increase, then the third path. So basically, if there is a fourth and fifth paths that were never assigned any flow, we didn't use those paths, but we used it in the traffic assignment, but we didn't use them in the weighing when we're using the weights. So replacing, and also the second thing we did was replacing the link-based, Frank-Wolfe algorithm with path-based algorithm, and we use gradient projection, and which is more efficient. It takes fewer iterations and so on. I'm going to talk a bit more about it. And potential problems is, okay, we did this adjustments to make it more computationally efficient, but do we still have similar rankings with the original LCI and with the adjusted approach? So if these two, when we adjust it, gives a completely different set of rankings, that means it's another measure now, and we cannot really tie it to the original one. And basically trade-off between using the full set of OD paths or a subset of OD paths, does it cost us the accuracy or consistency? And also, can we really get a computational reduction in computational burden? And for relaxing path enumeration, what we did was get rid of the path enumeration, but we keep track of the shortest path within Frank-Wolfe algorithm. This is a pseudocode for Frank-Wolfe algorithm. And at the very end, and we stored all intermediate iteration flows and all the data. And at the very end, we calculate the LCI as a post assignment by using the path list that we tracked and populated within the algorithm. And for use of gradient projection, relatively easier to implement, because GP algorithm already keeps a list of shortest paths within its design. And that's why we just add as a post assignment module where we use the shortest path list and all the changes in marginal cost and link flows to calculate these weights, and then accordingly calculate LCI. And we use 3 networks: Nguyen Dupuy network, Sioux Falls network, and Anaheim network. So basically a smaller, let's say one small, one more closer mid-range. I don't know how each one of you listeners would define what is large, what is small, but Anaheim network is the largest among these 3. So what to test? First, we need to make sure that original LCI, now I'm kind of putting more terms here. Original LCI, I mean the one with Frank-Wolfe and path enumeration. When I say Frank-Wolfe LCI, it's still Frank-Wolfe, but uses the viable paths, not the path enumeration. And GP is the same with, only using viable paths, but using gradient projection. One of our issues is, like, one thing we want to test is whether the original LCI, after we do the modifications and come up with Frank-Wolfe LCI and GP LCI, whether the rankings between those 3 match. Basically, are those measures identify the same set of links as the critical? And also compare them with the other criticality metrics. How do they compare with the others for different networks? And looking at, again, link flows versus criticality rankings. Basically, we're trying to shoot ourselves in the foot, because if we see a consistently, high correlation with link flows and criticality rankings, maybe it means that we don't really need to do this line of research, because, hey, let's look at the flows and just rank them, and this is our criticality ranking. So, and one of the things we also noticed within those tests and everything is ranking correlations for different levels of network congestion. Basic network congestion affects how these metrics agree or disagree, or they give the same level of rankings. It's actually discussed in literature as well. Like the network congestion levels is important when we're looking at link criticality. And comparison with the original LCI, meaning with the path enumeration, with other measures are done for Nguyen-Dupuy network and Sioux Falls. We didn't do it, actually we couldn't do it for Anaheim, because case in point, path enumeration for Anaheim network is computationally very costly. So we couldn't even run original LCI for an Anaheim network, which shows that the claim of original LCI being computationally like have computation advantages disappears as the network gets larger. For Sioux Falls, yes, maybe similar size networks, yes, it may be more, it may take less time to run it because there are not as many traffic assignments, but meanwhile, the path enumeration also blows up as the network gets larger. So we talk about consistency of rankings. How do we measure the consistency? In the previous example, I showed you the locations, like in rankings of each link, and by basically hand waving, so to speak, we say, oh, this is on the top, this is on the bottom. So how to do it more rationally? So we use Spearman's rank coefficient. It's very close. It's somewhat close to, not very close, somewhat close to Pearson's correlation coefficient, which looks at the linear relationship between values. But Spearman's rank coefficient assesses monotonic relationship, and it doesn't matter if it's linear or nonlinear. And it takes values between -1 and +1. Actually, -1, +1, it's something like elasticity from economics. Minus tells you the direction of change, and with closer to 1 or -1 means high correlation, but negative correlation implies that as the rank of the one variable increases, the rank for the other decreases. But other than that, -1 and +1 shows perfect correlation between two, but just in the opposite directions. And there is no like a tableau that tells you, okay, between these values is good correlation or not. It's very domain specific, but we looked at few sources, and we used the notion that between 0 to 0.2 it's very weak, and it's almost going 0.2 increments, and 0.8 to 0.1 to be very strong, and so on. So flow ranking versus critical score ranking. So if we first looked at how does the flow is correlated with the criticality scores for Nguyen-Dupuy network, we have uncongested. What do we mean by uncongested, semi-congested, congested? For the uncongested one, volume over capacity for all links are lower than 1. For semi-congested, 26% of the links have lower, volume over capacity lower than 1. And for congested, all links have volume over capacity larger than 1 in the equilibrium. So for the uncongested network, we have a very high correlation with the flow ranking and ranking by each criticality measure. It's like almost, perfect, except original LCI. There's a huge discrepancy between the adjusted version and the original version, and between the centrality too. Between centrality has very low correlation with the flow, which is expected because between the centrality does not even, there's no flow anywhere in calculation of between centrality. It's a topographical measure. It just looks at how many times a link appears in the shortest path between ODs in the network. And for semi-congested and congested networks, there is an decrease in correlation. So basically, as the network gets more congested, for at least Frank-Wolfe LCI and GP LCI, the correlation with the flows get lower. Basically, when it's uncongested, there's a higher correlation with the flow. When it gets more congested, there's a lower correlation with the flow. This is almost the same for all the others. Like there's a decrease, but for instance, for NRI and IS, there's a decrease from uncongested to semi-congested, but then semi-congested to congested, there's a slight increase. You may even say they're almost equal, but there's a slight increase. And for travel time between the centrality, there's a huge drop, similar to Frank-Wolfe LCI and GP LCI. And here, again, between the centrality and original LCI has like increases and decreases. Between the centrality increases, but still very low. So there is not really a direct comparison. And when we look at the final, where the congested, the correlation with the flow, for Frank-Wolfe LCI and GP LCI still is not as highly correlated compared to the other select measures. Only different being travel time, it means weighted between the centrality. And if you look at Sioux Falls network, the decrease is very high, and also we lose the kind of agreement between the Frank-Wolfe LCI and GP LCI. In Nguyen Dupuy network, we have a good agreement between the adjusted measures, but only thing either with Frank-Wolfe or gradient projection, they're almost identical, sometimes very close, like 0.46 and 0.45. But in the Sioux Falls network, we also lose this agreement between two adjusted versions of original LCI. And here, the difference is even higher. And if you look at the other methods, and AI, NRI, and IS, correlation with the flow, as congestion increases, they increase. And in Nguyen Dupuy network, they decrease as the congestion increased. So there's like always conflicting findings. And when we look at the consistency of the original, that's something we want to make sure, right? We want to make sure that original LCI gives more or less same rankings adjusted. And here, rankings correlations range from moderate to very strong. So there is kind of a good agreement, especially if it's congested. Ranking consistency affected by network congestion. Correlation increases as network congestion increases. And as you see, there's like an increase in correlation of adjusted LCI with the original LCI. And it's same for Sioux Falls. Because of the reason for that is because for original LCI use path enumeration. For other ones, it uses the paths that are on the shortest path within the iterations of use equilibrium. So as the network gets more congested, more links, more paths are added to the shortest path link, because the demand is so high that more alternative routes are used. So in theory, as you increase the demand more and more in the network, you're getting to the same path list as the enumerated paths, because all paths between all ODs become shortest path at some point. So that's why it's expected from how LCI is formulated. And increase in ranking correlation is higher for Frank-Wolfe LCI. But the issue is also always Frank-Wolfe LCI is higher. Gradient projection is faster because it goes through few iterations. So one is more highly correlated, but the other one is faster. So original LCI and other metrics. Generally, there's no consistent relationship. Like it may go up, down, sometimes jumps. If anything, congestion correlation pattern is network specific. So we see different patterns in different networks. And there is negative correlation between the centrality and travel time weighted between the centrality at Sioux Falls. So original LCI has a negative correlation between the centrality related measures at Sioux Falls. And if you look at Anaheim, now we don't have original one. I want to just very quickly go over a few things here. First, if you look at two versions of the adjusted LCI, they agree very nicely, let's say, it's almost perfect. So, and if you look at the flow, how they are correlated, it's also high. If you look at how they are correlated between the centrality, it's decent as well. It's like moderate to high. And I'm specifically talking about between the centrality because it's a topographical measure. So LCI shows a good correlation with the flow and also good correlation with a purely topological measure. If you look at the other methods, there is all the other methods also have a good correlation with flow, except between the centrality, which shows that between centrality and flow are not related, but somehow LCI is highly correlated with flow and between the centrality separately. So if you look at the between the centrality and the others, it's very low. It's in the opposite direction, but even then it's a very low correlation. And for the computational performance, Runtime for Anaheim with Frank-Wolfe LCI is 138 seconds. And for the other methods, when removing each link and doing the assignment again, it is 100,000, 111,000 something. So runtime savings are in the order of number of links. I mean, 138 seconds, 914 links for Anaheim network. Anticipated time would be multiplying them 126,000 something. It's a bit less because this 138 seconds will change based on, the one run, user equilibrium run, will change based on which link you remove. Some it will take fewer iterations, some will take more iterations, depending on which link you remove and how the algorithm converges. So, but eventually the difference is in the order of magnitude. So instead of running n times for a network size of n links, we can do it all at once. So as the n increases, the computational efficiency of adjusted LCI improves. And very encouraging, especially thinking that gradient projection gives even better runtime results. This was the worst case with Frank-Wolfe, which has worse runtime than gradient projection. And summary, mostly yield consistent ranking. Choice of algorithm didn't matter for Anaheim network. Both Frank-Wolfe and GPLCI have strong correlation with link flows. And also, this is the same for other metrics. Correlation between centrality are also higher compared to other approaches. Relatively strong for Frank-Wolfe and GPLCI, but between central has very weak correlation with the other methods. I'm saying this because between central has a topographical measure which tells that the other metrics don't incorporate the topographic issues as much, which may be overstating based on one topographical measure, but we also work on it. So I will show you one more slide. Findings may support the argument that the Frank-Wolfe LCI and GPLCI provide balanced ranking that considers connectivity redundancy, basic network topology, and also traffic conditions, for example, flow simultaneously. So as we have more results, we have more questions. Frank-Wolfe and GPLCI, they worked fine. They agreed between each other, but they didn't agree for Sioux Falls. Why? Like why they agree that Sioux Falls but didn't agree in Anaheim network? What characteristics does Anaheim network make these two rankings agree more? And for that matter, how does network topology affect any set of metrics to agree or disagree more? Like I'm just showing, there are other metrics, or sometimes they agree more for some networks and they show different directions in other networks. What are the topological, measures of what are the network characteristics that leads to this discrepancy or agreement? And also network congestion levels affect consistency between Frank-Wolfe LCI and GPLCI, and it's also the same for the agreement in other metrics as well. And there's a fundamental and practical question. If you were the planner or policymaker and you're asked to find which is the most critical link, which measure are you going to use? Like, because each one of them shows something else. It's good to know maybe there's a weighted average of metric bundle. You take half of this measure, 25 of this measure, like a recipe. But is this recipe same for all networks, or depending on network topology, this bundling also changes? Or should we just skip all the trouble and look at the link flow levels? Like, this is a very important question because this may not be relevant if everything comes out to be highly correlated with link flows. So I'll show you, with the last slide, I'm going to show you a sneak peek. I'll say fresh from the oven. It's almost literally, I asked from Amir to send this to me yesterday. So basically what we're doing right now is we're trying to understand how to approach, answer those questions that I asked. In this graph, you see LCI versus link flow. We're looking at the correlation coefficient for different networks. We basically created random networks, which we made sure that they look like they're not purely random, but when we look at them visually, they also look like transportation networks. So we arranged random networks with different transitivity metric as the network measure. And as the transitivity metric increases for the network, basically each dot shows the correlation between LCI ranking and link flow ranking for a network. So each one of the dots is a different network. As you see, each network is a different transitivity value, and correlation coefficient is different between the LCI and link flow. And we did it for other measures as well. You know, IS and link flow, LCI versus IS, the importance score, one of the measures that we used before. And also we did this for other measures, like network efficiency. How does it change with network efficiency, whether they agree or not at certain range? And for instance, what we're looking at now is what type of network topologies result in agreement or disagreement of criticality metrics, how or whether to bundle them. Or let's simply say again, if your network transitivity is about 0.4, use link flows, because what we see there is whatever you calculate with LCI or importance score, it agrees very highly with the link flow. So why bother calculating, doing all this rigorous math? So these are our related publications on this, the work I presented you here. I had to skip so many parts. Probably from this publication, you may have a better idea of some details, and that's it. I was a bit off time, I think, over time.
No, you're doing great. We still have a few minutes for questions, actually. So first, thank you very much. That was a great presentation. And I'll open it up to participants now. If you have any questions for Professor Yazici, please write them in the chat box below and I can start to read them out. Okay, we have one question. Okay. So, do you think travelers' experience on the link's importance will be dynamic as the network status may change daily? For example, work zones. If, for another example, if an express route you use for a commute was temporarily unavailable, let's say for a week, there may be a natural shift to another route which was ranked less highly, but is now the most important one after the change. It was a long one. Did you get all that?
Yes. What I can tell is this relate for, okay, that was actually another discussion that we're having, whether this criticality is like a static measure, like there's a network and there are critical links and that's it. But we see that congestion levels, as the congestion level change, the rankings of critical links also are affected. And this relates to if there's a work zone somewhere, if one link is removed, then the other links are utilized more. As much as the model can, do this, that's why like the reason we moved away from link removal is to incorporate these, the impacts of link removal. A work zone, a link is closed, then everybody goes to the other routes, and all of a sudden, the routes that you never used, you're using it daily and becomes critical. We try to incorporate these links without the link removal. Link removal makes it directly, very harshly. Okay, you remove the link, you know which ones become more important. But what we're trying to have is looking at alternative routes. For instance, if you remove the route, like road is closed, and the alternative was only, instead of 15 minutes, the alternative was 20 minutes, and all of a sudden it becomes your only option, then we try to put more weight to foresee that if the other one fails, this closer travel time path is the next viable one. So we try to incorporate those, and I agree, yes, the link criticalities will change based on how the network is. If the topography changes, for sure. But even if topography changes, there is no link removal, all the routes are functional. As the demand level changes, the route that is critical during, even for rush hour peak direction and on the evening peak may be different.
Okay,
actually,
so
we saw that it's different. When you change the demand levels, the link criticalities change.
Okay, that actually gets to our second question, which deals with differences in times between like morning and evening rush hours. Mm-hmm. So other than flow and network topology, is there any way to incorporate other behavioral factors of travelers into the determination of the criticality? Like, for example, constructing a probabilistic criticality?
That is a good question. For the way I see it is in the use, I mean, the way that we're approaching it, I'm sure there are like ways, and it's a good topic to pursue, but within the way we formulated LCI, one way to incorporate it, I believe, would be looking at user equilibrium, playing with how the assignment is done, because now we're using the user equilibrium assignment, iterations where a flow is assigned to the shortest path and so on and so forth. So to do that, if one way or another, this kind of stochastic behavior of users, or maybe it may be perceived, it could be stochastic user equilibrium could be used, and LCI can be incorporated into that, because eventually we're not tweaking anything in the code. We're just adding this modules in between the iterations to get the LCI. So I believe stochastic user equilibrium will be one way to incorporate this stochasticities within the way we formulate the LCI. That's, I can answer back of my head.
Okay. What if you removed 2 links instead of 1? Would maybe we'd see an effect that could be nonlinear?
Actually, there is something that, in the most of the work in the literature is there, it's 1 link removed and ranking is there. What we're trying to actually, the reason we were trying to find a computationally efficient algorithm, like efficient method doing this, is to be able to test those kind of scenarios. Because in toy networks, you can do this like 1 link, 2 link, but we want to be able to look at how LCI compares with 1 link removal, 2 link removal, because 2 link removal will require you remove 1 link, then combinatorials of it. Like you remove 1 link, then move all the others one by one. It just blows up. The number of user equilibrium iterations so high that the study, even if you have a metric which works with link removals, it won't be able to complete a large network. You remove 1 link, you remove 1 link and then 1,000 links for the first combination. Then you remove the second link, another 1,000 links. You have to do like, factorials of, combinations of assignments. So with LCI, now we have, a relatively efficient way to figure out the criticality. We want to look at how this 1 link removal, 2 link removal, multiple link removals, not even 3 maybe, how it will affect how the rankings will change that way. That is kind of our future research direction, which I didn't mention here.
Okay. And also, so if you don't use user equilibrium assignment and you assume system optimal assignment, that changes the ranking as well. Does that?
We didn't try it, but I'm sure it will, because like because user equilibrium, principle is very different than system optimal, and we actually wanted to go this path, but the way that we see is kind of ripe area of research in terms of multiple link removals. What if we change not user equilibrium but system optimal? So we're now staying in the system, so user equilibrium part, and trying to figure out like, how network topology affects the rankings. I mean, for LCI and for others too. We're curious. We want to, formulate a very good metric. We did up to a point, but we also want to see how, in general, metrics behave in different network settings, and also looking at multiple removals. But system optimal part, we're not really pursuing it at the time. But it will be a good research direction as well.
Okay, I have 2 more for you. So
Okay.
what about looking into other metrics like closeness centrality, eigenvector centrality?
We're actually now within this, the last sneak peek that I showed you, we're looking at how this topological measures relate with the LCI, because most of the time topological measures don't take into account flow. So we try to compare mostly with other metrics that use traffic assignment or use one way or another the traffic flow in their criticality rankings. And we only use between the centrality, which was the to be honest, like one of the first things that everybody has familiarity with. But we are now looking at, with this random network generation, we're looking at different network topological measures and how the network topology affects the rank, like how they correlate with the rankings. We're looking at few other, I showed, I think, transitivity and efficiency, but we have few others, including other centrality measures, to see how they correlate with the rankings.
Okay, and the last question I have for you, so you got into this a little bit at a previous question, but since the LCI is so computationally expensive, how do you see it applying to a real network potentially much larger than like Anaheim?
The thing is, for now, because we don't do any, like within the new version where we get rid of the path enumeration, the additional burden, there's no additional burden to the, except that keeping track of the shortest path, there's no additional burden. So if you have a network, especially for if you use gradient projection, then it's even easier because it keeps the track of shortest path. So basically, if you have a network that you can run and get the results for usual equilibrium traffic assignment, you can calculate the LCI, but not the original version with the path enumeration. But the second one, if you can run one usual equilibrium, so basically, if you have a very large network and you cannot run usual equilibrium, yes, I can, LCI cannot give you ranking. But if there's any network and you can run usual equilibrium, worst case, the GP, gradient projection one, will give you. I'm saying this because if there's a concern about this increased memory allocation for in Frank-Wolfe when you add more and more shortest paths. Apart from that, both Frank-Wolfe LCI and GP LCI will provide you the rankings if you can run and get the results for the network.
Okay, I think that's time. So thank you so much for joining us today and for your great presentation. And thank you to the participants for asking lots of great questions. Just a reminder, you can check this out. This will be recorded on the C2 Smart YouTube channel. We hope you'll join us for a future seminar.
Thanks everyone for listening.
Yeah, thank you.